Hello, and welcome to Nature Nights with Atty. It's good to have you here. Wherever you are tonight, settle in and get comfortable. Take a deep breath and let it out slowly. There's nothing to do from here and nowhere to be. Tonight, we're in the Amazon rainforest. The dry upland part of it, the ground that never floods. That's most of the forest, and the part you're least likely to have seen. Over the next few hours, we'll follow a single day there, from the dark before dawn, round to the dark on the other side. There are ants down there that farm a crop underground. A sloth that grows its own food in its fur. A bat that hunts fish by reading the ripples on the water. And trees that put more water into the sky each day than the river carries out to sea. All of it comes from published research. Where the researchers disagree, you'll hear that said out loud. And a few of the best-known facts about this forest turn out not to be true, so those get put right along the way. Let your thoughts wander wherever they like. If you'd like more nights like this one, a subscribe is what keeps them coming, and it's how a quiet channel gets found at all. Let's begin where the forest begins, with the ground it stands on. The Amazon basin drains close to 7 million square kilometers of South America. That's the watershed. Every river, every stream, every wet hillside whose water ends up leaving through the same mouth. It's the biggest number attached to the word Amazon, and it's the one usually meant when the forest gets measured. The forest is smaller. Continuous rainforest covers something over 5.5 million square kilometers inside that watershed. Most of it never floods. There are belts of flooded forest along the biggest rivers, underwater for months at a time, but they're the exception. The ground between them is where all of this takes place. Terra firm ground is the high rainforest that sits above the furthest the water ever comes. It's dry underfoot all year round, and it's the ground under everything that follows. That difference matters more than it sounds. Where the water reaches, the forest turns into a water world for months at a time, with its own trees and its own animals. Terra firma is the other one, the same latitude, the same rain, and a floor that stays where it is. The ground is rarely flat. It rises and falls in low ridges and shallow valleys. 9 countries hold a piece of it, and by far the largest share is in Brazil. Then Peru, Colombia, Bolivia, Ecuador, Venezuela, Guyana, and Suriname. The 9th is French Guiana, which is not a country, but a part of France, and that means the European Union has a land border with the Amazon rainforest. Rain across the basin comes to somewhere near 2,200 millimeters a year, though the average hides the more interesting part. In the north and northwest, up near the Andes, 3,000 millimeters is ordinary, and the Andean slopes take a good deal more than that. In the south, parts of the same basin get closer to 1,000. There's no single rainfall figure for the Amazon. There's a slope from one end of it to the other, and the forest changes along it. Whatever falls has to leave again. The river pours out an average of 209,000 cubic meters of water every second. Somewhere between 15 and 18% of all the fresh water reaching the world's oceans comes out of this one mouth. Some measurements push it closer to 1/5. The number shifts depending on how it is measured, and the size of it does not. Numbers that big stop meaning very much on their own. The simpler version is that all of it arrived as rain, fell through leaves, and found its way downhill. The forest keeps 2 seasons rather than 4, a wetter one and a drier one. The drier one is still wet by most standards, and the temperature barely moves across the year. The calendar here is made of water instead of heat. Nearly every species count in circulation traces back to a single inventory put together in the mid-2000s. Repeated often enough, an estimate starts to sound like a census. By that count, the forest holds at least 40,000 kinds of plant, about 3,000 freshwater fish, and around 1,300 birds. Then 427 mammals, 428 amphibians, 378 reptiles, and 16,000 kinds of tree. Those are flaws rather than totals. New species get described here all the time, fast enough that the published lists are out of date almost as soon as they're printed. The honest version is that nobody knows the total, and the not knowing is itself a fact about the place. Airborne laser surveys put the average height of the canopy at just over 22 meters. That's about 7 stories of air between the ground and the roof. Individual giants stand far higher, and an average like that folds them in with a much larger crowd of ordinary trees. The roof isn't flat. From above, it looks like a rolling surface, dented where trees have come down and lifted where one old tree has grown out past its neighbors. That roof usually gets described in layers: emergent, canopy, understory, floor, 4 of them drawn in every diagram. Laser measurements from satellites have mostly taken that picture apart. Across the Amazon canopy they sampled, about 79% of the readings show a single thick band of vegetation rather than 2. It reads as one mass, thickest near the top and thinning downward, without the shelves the diagram promises. Layering is real, but it's real in a minority of the forest rather than all the way through it. Where it does show up, it tends to be somewhere the ground was disturbed, an old gap, a river edge, a patch that fell and grew back unevenly. So that's the shape of the place. 5.5 million square kilometers of forest, most of it standing above the waterline. A roof averaging 22 meters, thinning downward rather than stacking into shelves. Rain that varies threefold from one edge of the basin to the other, across 2 seasons. 16,000 kinds of tree, and an unfinished list of everything living among them. The hours ahead run through a single day of it, on dry ground, under that roof. Before first light, the floor of this forest is very dark, and it stays dark for a while after the sky has stopped being dark. Only 1 or 2% of the sunlight landing on the top of the canopy ever reaches the ground. On a bright afternoon, that's enough to see by. In the half hour after the sky begins to grey, it isn't. What light there is comes from the sky rather than the sun, and it filters down through several layers of leaves before it arrives, losing most of itself on the way. Down here, dawn doesn't break. It seeps. The air is at its coldest now, and the cold came down out of the canopy. All night the top of the roof has been giving off heat into open sky. The leaves and branches up there lose their warmth fastest, because they're the part of this forest actually facing space. The air touching them cools. Cool air is heavy air, and heavy air sinks. It slides down through the crowns, reaches the ground, and then keeps going downhill, following the shape of the land the way water would. It collects in the low places. That's where the fog is. Not spread evenly through the forest, but pooled in valleys and hollows and old streamlines. It lies in a layer with clear air above it and the ridges standing out of it like islands. Because it's there most mornings, it changes what grows there. Valleys that fill with fog carry more kinds of epiphyte than the drier slopes just above them. More orchids, more bromeliads, more of the mosses and ferns that live on bark instead of soil. Those plants are keeping a record of where the cold air goes. A map of the fog would be a map of what grows where. On the leaves themselves, something switches over. All day and through most of the night, a leaf loses water. It opens its pores, water evaporates away, and more is drawn up from the roots behind it. That's the normal direction, and it only runs one way. Late in the night, the direction reverses. A leaf giving off heat to the sky cools below the temperature at which the air around it can hold its moisture, and water starts to condense onto the leaf instead of leaving it. The leaf stops being a source and becomes a surface. It adds up to more than it sounds. Across a forest, this puts about 0.8 of a millimeter of water a day onto the leaves, and none of it fell as rain. It's water the forest takes straight out of the air by being colder than the air. Every night, for nothing. The ground under all of this is easier to walk on than its reputation suggests. There's no wall of vegetation. Under closed canopy, the floor is largely open, leaf litter, roots, the trunks themselves, and enough space between them to move without cutting anything. The dense green tangle is real, but it belongs to riverbanks, forest edges, and light gaps, which is where enough light reaches the ground for low plants to grow thickly. Under a closed roof, there isn't enough light down here to build a wall out of, which is convenient for something large that wants to move through it in the dark. The lowland tapir weighs up to about 300 kilograms, which makes it the largest land mammal in South America. It doesn't look built for quiet. It has a barrel body on short legs and a short flexible trunk, and it moves along the same worn routes through the understory, mostly at night. Something close to 9/10 of its activity falls between 6 in the evening and 7 in the morning. It leaves a deep print in soft ground. So this is the end of its shift rather than the beginning. By the time the birds start, it'll be lying up somewhere dense and dark, and it won't move again until the light goes. What it's been doing all night matters more than it appears to. A tapir eats fruit, and at that size, it can swallow seeds too large for anything else in this forest to handle, then carry them for hours before they come out somewhere else entirely. Very little else here can move a large seed a long way. For the biggest seeded trees, the tapir isn't one animal among several. It's close to the only one. It also keeps doing the work in places where the forest has been damaged. In burnt forest, where most large animals have gone, tapirs are still moving through and still leaving seed behind them. Whatever regrowth happens on that ground starts, in part, with an animal that never stopped walking its route. The fog is still in the valleys. The dew is still on the leaves. Somewhere above all of it, the sky has begun to change color, and down here nothing has noticed yet. The chorus doesn't build. It's commonly pictured as a swell, with the whole forest waking together, and that isn't what happens. For 2 years, recorders left running around the clock in the eastern Brazilian Amazon listen to when things actually call. Insect noise peaks between 8 in the evening and 5 in the morning. It's at its lowest between 7 in the morning and 3 in the afternoon. So the insects aren't joining in at dawn. They're finishing. What happens at first light is one shift handing over to another. For an hour or so, the two overlap, and the forest is louder then than at any other point in the day. Not because everything is waking up together, because two different crowds are briefly in the same room, one of them arriving and one of them going to bed. Among the birds, the order they arrive in isn't random, and it isn't really about light either. What decides when a species starts singing, more than anything else, is how high up it feeds. Canopy birds begin around 44 minutes before the ones that feed on the ground. The higher up a bird lives, the earlier the light reaches it, and the earlier it starts. So the chorus builds downward. It begins in the crowns, arrives in the middle of the forest sometime later, and reaches the floor last, which means anyone standing on the ground hears the whole thing coming down towards them. Eye size comes into it too. Birds with larger eyes for their size sing earlier, because a bigger eye gathers more light and gets a usable picture sooner. What that picture is for is the interesting part. It isn't enough light to hunt by. It's enough light to see a predator coming. That's the thinking behind what's called the inefficient foraging hypothesis, which is a long name for a simple idea. In the half-light before sunrise, a bird can't feed properly yet. There's too little to see by, and hunting in that state uses up more energy than it brings in. But there's enough light to be reasonably safe, and cool, still air carries. So the gap gets filled with the other things a bird needs to do: hold a territory, find or reassure a mate, and announce that it survived the night. Song is what fills the hour before feeding is worth the effort. There's also something in the family tree that neither explanation covers. Suboceans, the antbirds, the flycatchers, a huge group in this part of the world, sing earlier than the oceans. That still holds after allowing for how high they feed and how large their eyes are. Something about the group itself sets the clock differently, and nobody yet knows what. The explanation given most often is the one about air. Dawn air is still and cool and carries sound better, so birds sing then because it's when they're best heard. That isn't wrong. It's just not the whole story. The air really does change overnight, and sound really does behave differently in it. But when researchers test which things actually predict the timing from one species to the next, social pressure and diet predict it better than sound does. The physics is real. It simply isn't doing most of the work. Underneath the birdsong, every so often, is something that isn't birdsong at all. A howler monkey roar carries about 4.8 kilometers through this forest. That's not a shout. A shout doesn't travel 5 kilometers through 5 kilometers of standing trees, and the trick isn't lung power. It's bone. Howlers have a hugely enlarged hyoid, the small bone that in most mammals just anchors the tongue. In these monkeys, it's turned into a hollow, cup-shaped chamber of solid bone sitting in the throat, and it works as an echo chamber. Sound made in the voice box passes into it and comes out louder and lower. It's the same principle as a brass instrument, where the body of the horn does far more to the final sound than the player's lips do. The chamber is much larger in males than in females, which fits what the noise is for. What the noise is for is boundaries. The dawn roar isn't a general announcement to the forest. It happens at the edges of a group's territory, and it works as border defense. Neighboring groups roar at each other across a line, establish that both are there and both are in position, and then don't meet. It's an argument settled entirely at a distance, and it works when nothing happens. The sound doesn't resemble a monkey at all. It's low, continuous, and mechanical, closer to wind across the mouth of a bottle scaled up several times, and it arrives from a direction rather than from a place. A group can be half an hour's walk away and sound as though it's in the next tree. A quieter version of the same idea is going on nearby. Coppery titi monkeys live in pairs, and at dawn, a pair sings together. Not two animals calling at once, but a proper duet, each partner taking particular parts and fitting them around the other. Over time, a pair works up a version that's distinctly theirs, and the neighbors learn it. The surrounding groups can then tell exactly which pair is singing, and roughly where they are. It's a fence made of sound, rebuilt every morning, and it works for the same reason the howlers does. Everyone knows where everyone is, so nobody has to find out the hard way. Not everything greets the morning with confidence. For the small monkeys, the marmosets and tamarins, animals weighing a few hundred grams, the risk is stacked into the morning. The hours between 5 and noon carry the highest chance in the whole day of being taken by a hawk or an eagle. The light that lets them move is the same light that lets a hawk see them. So coming out isn't eager. It's careful and slow, and involves a great deal of sitting still and looking upward before anything commits to going anywhere. Where they spend the night comes down to the same thing. The sleeping trees they prefer, in one study, average 22.5 meters tall, with the first branch about 10.5 meters off the ground. That's a long, smooth column with nothing to grip on the way up. The shape of it isn't about comfort. It's a moat. Anything that climbs has to cross 10 meters of bare trunk to reach them, and crossing 10 meters of bare trunk takes long enough to be noticed. Lower down, in the understory, nothing is flying yet. A butterfly can't simply decide to take off. Its flight muscles won't produce any useful power until the middle of its body is somewhere near 29 degrees, and at dawn, it's nowhere close. So the first thing a butterfly does in the morning is warm itself up. Some spread their wings flat to catch whatever direct sun they can find, angling to the light like a panel. Others shiver the flight muscles without moving the wings at all, working them against one another purely to make heat. It's an ignition temperature in the ordinary mechanical sense. Below the number, nothing happens. Above it, flight. Which is why the first patches of sun to reach the understory tend to have something sitting motionless in them. It looks like an animal doing nothing. It's the only thing that matters. The fog in the valleys is beginning to lift, or rather to be burned off from the top down. Most of the insects have stopped. The last of them will still be going when the sun clears the canopy, and by then the birds will have been at it for an hour. The morning belongs to the top of the forest, so that's where this goes next. Where there's a true emergent layer, the giants that make it up break through the general roof somewhere between 45 and 70 meters. They aren't the norm, and they don't form a continuous layer of their own. They stand alone, or in loose scatterings, with open sky around their crowns, and the rest of the forest below them. The tallest one ever confirmed in the Amazon is Adverts excelsa, measured in the state of Para in 2019 at 88.5 meters. That's very nearly 30 meters above the previous Amazon record. A jump that size isn't a small step up. It's an admission that nobody had properly looked. It was found by laser survey from an aircraft in forest that had been flown over for years. The roof those giants punch through is thinner than it sounds. A closed canopy is a layer of leaves and branches only about 3 to 12 meters deep. Everything above it is air and emergence. Everything below it is shade. From a distance, the forest looks like a solid green mass, and the working green part is a skin stretched over a mostly empty space. There's a ceiling on how tall any of it can get, and the reason for it is plumbing. A tree doesn't pump water upward. It pulls. Water evaporating from the leaves at the top tugs on the whole column of water below, and that pull drags the next water up behind it, all the way from the roots. It works because water molecules hold onto each other tightly enough to be dragged up in one continuous thread. But a thread under that much pull can snap. Past a certain height, the pull gets strong enough that the water column can break apart into vapor, forming a bubble that cuts off supply to everything above it. The ceiling that works out from this is somewhere around 122 to 130 meters. No tree anywhere on Earth has beaten it. The limit on how tall a forest can be isn't strength or wind or lifespan. It's how hard water can be pulled before it comes apart. Looking up through the crowns, there's a pattern that's hard to unsee once noticed. The outermost branches of neighboring trees don't touch. Between one crown and the next, there's a gap, often quite even, tracing the outline of each tree in open sky. It's called crown shyness, and after decades of study, there are still two competing explanations and no agreement. The first one is about contact. Crowns in wind knock into each other, and the knocking wears the growing tips off the outermost branches, so each tree gets pruned back by its neighbors to exactly the distance where the contact stops. The second is about light. Plants can sense the balance of red to far red light, and light that's passed through a leaf has had the red taken out of it. So a branch tip coming up on another crown can tell a neighbor is there before it touches, and stop growing that way. There's a good experiment on the contact side. When tree crowns were roped in place to stop them swaying, the crowns grew larger and started to interlock, which is what would happen if the knocking had been doing the pruning. That's real evidence, but it doesn't settle it, because the two explanations don't rule each other out, and both could be happening at once. The branches themselves are a habitat, and this is the part that most changes what the canopy is. Dead leaves, dust, bark, fallen debris, and the rotted remains of earlier plants pile up on flat branches and in the forks of big trees. Given enough decades, it turns into actual soil that holds water and that roots can grow into 30 meters up in the air. In one old forest that had never been cleared, it was measured at something like 20,000 kilograms per hectare of material held up in the branches. Nearby forest that had grown back more recently and hadn't had the time carried roughly 5 kilograms per hectare. Those particular figures come from mountain forest in Costa Rica rather than Amazon lowland. The matching Amazon numbers aren't as well established, so it's the size of the gap that counts here rather than the exact amount. The trees have noticed it. Some of them grow roots straight out of their own bark, up into the mats of soil sitting on their own branches, and feed from them. A tree drinking from material that piled up on itself through roots that grew out of its trunk into open air. It isn't a rare oddity. It's a normal way of getting by up there. What lives in that soil is the epiphytes, and epiphytes aren't a side note. Plants that grow on other plants without ever touching the ground make up around 10% of all the plant species on Earth, with veins in them. In wet tropical forest, they can be a quarter to a half of all the plant variety in the area. By weight, epiphytes come to around 44 tons per hectare, and if the wood of the trees themselves is set aside, they're more than 80% of everything living up in the canopy. Some of them hold water. Tank bromeliads have leaves arranged in a tight rosette that funnels rainfall inward and keeps it, and across a hectare of forest, the bromeliads together can hold up to 50,000 litres. That's a wetland, split between thousands of separate little containers, hanging 20 to 30 metres above dry ground. And where there's standing water, there are frogs. Poison frogs breed in those tanks, and they're a great deal fussier than just finding water. A male will carry eggs to one leaf crook and tadpoles to a different leaf crook on the same plant. He chooses between them by depth, by how much water is in each, and by what's dissolved in it. The different stages need different things, and the frog is checking them one at a time. He isn't picking a plant. He's picking a pool out of the several dozen pools one plant offers, which makes a difference to which trees are left standing. The largest and oldest emergents carry the biggest, oldest, steadiest loads of epiphytes, and so the biggest and most reliable tanks. A single tree like that can't be stood in for by anything younger, because what the frogs need isn't the tree, it's what has piled up on it, and the piling up takes a lifetime. Taking the oldest trees out of a forest removes far more frog nurseries than their numbers suggest. Not everything up here waits for water to collect. Orchids growing on bare bark solve it a different way, with a tissue called the velamen radicum. It's a spongy layer of dead cells wrapped around the roots that hang in the air, and it soaks up water on contact within seconds. Just inside it sits a waxy layer that stops the water getting back out. The root works as a sponge with a one-way valve, and it works fast because rain in this forest is heavy, brief, and gone. There's an animal in these crowns running the strangest arrangement in the forest. A sloth carries algae in its fur. The hairs are grooved to hold moisture. The algae grows in the grooves, and the sloth is greener than it looks from a distance. It also carries moths, a species that lives nowhere else on Earth except in sloth fur. The moths breed in sloth dung. When a sloth climbs down to the ground to go to the toilet, the female moths leave the fur, lay their eggs in the dung, and the young develop there. The new adults then fly up into the canopy and find a sloth of their own. Moths that die in the fur rot down where they lie, and rotting moths give off nitrogen, which feeds the algae, in a place where nitrogen is otherwise very hard to come by. And the sloth eats the algae, grooming it out of its own coat. In the lab, that algae turned out to be up to 5 times richer in quick-burning fats than the leaves that make up the rest of the animal's diet. Which puts the thing sloths are best known for in a different light. About once a week, a sloth climbs all the way down to the forest floor to go to the toilet. It does it slowly, on the ground, where it can barely move, and where almost everything that kills sloths is waiting. It's the single most dangerous thing the animal does on any kind of schedule, and it has always looked like a quirk nobody could explain. It's the step that makes the rest work. Without the climb, down the moths can't lay. Without the moths, there's no nitrogen. Without the nitrogen, the algae doesn't grow. and the sloth loses the richest food it can get at. The weekly risk is the price of the fertilizer. The leaves overhead come with a story attached, and the story is mostly wrong. Almost every tropical leaf ends in a drawn-out point, the drip tip. It's commonly explained as a way of shedding water fast to stop fungus and algae taking hold on the surface. That part has been tested. A field study cut the tips off living leaves and compared how much fungus grew on them against leaves left alone, and after 11 months found no real difference. The shape still does something. Leaves with drip tips dry faster. Drip tips are longer where the rain is heavier, and they change as a tree ages. A feature doing nothing at all wouldn't behave like that. So the shape is real, and it responds to conditions. It's the neat explanation for it that hasn't held up. The leaves also differ enormously depending on where on the tree they sit. Leaves at the top, in full sun, are thicker, waxier, darker, and hold more pigment for their size. Leaves in shade a few meters below them are none of those things. Same tree, same genes. The tree is making two different products for two different jobs. At the very top, the forest is doing something nothing can see. Amazon trees give off isoprene, a light gas that evaporates easily, and how much comes off depends on light and heat. At night, it's essentially nothing. As the morning goes on and the sun climbs, it rises steadily, peaking around midday. The Amazon is probably the biggest natural source of isoprene on Earth. Up there, the gas is chemically busy, taking part in how clouds form and in the chemistry of the air above the basin. So there's a second sunrise happening up here that nothing can see. Not light or sound, but a chemical breath rising off the whole canopy at once, starting from nothing at dawn and building through the morning. The animal life up here is mostly small and mostly not where the textbooks put it. The famous number came from Terry Irwin, who in the 1980s sprayed insecticide fog into single canopy trees, collected what fell out, and scaled the result up. He arrived at an estimate of 30 million insect and spider species worldwide. It was hugely influential, and it has since been revised a long way down. Most estimates now sit somewhere between 5 and 10 million. A steadier figure comes from a single Amazon study that sampled insect activity at heights up to 32 meters and found around 60% of it happening at 8 meters and above. That's a measurement rather than a guess scaled up, and it supports the modest version of the idea. The canopy, not the floor, is where most of the insect life in this forest is. Some of it gets around in unexpected ways. Knock a cephalot's ant off a branch, and it doesn't simply fall. It rights itself in the air, steers backward, rear end first, spots the trunk of the tree it fell from, and glides to it, landing on the bark better than 8 times out of 10. It has no wings. The whole thing is done with the way it holds its body and the flattened shape of its own legs and head. The steering was worked out by taking parts off and seeing what broke. Removing the hind legs sharply reduced how well they glided, which makes those legs the steering. An ant falling from 40 meters has an 80% chance of ending up back on its own tree, and it does it backwards. Above all of this, in the emergence, is the thing everything else in the canopy is watching for. Harpy eagles nest in the tallest trees they can find, usually around 40 meters up, and build a platform roughly 2 meters across out of 300 branches or more. The same nest gets used for years. The rear talons are 8 to 10 centimeters long, about as long as the claws of a grizzly bear. The bird carrying them hunts by flying through the canopy rather than above it, taking monkeys and sloths straight off the branches they're sitting on. Females can weigh up to twice as much as males. How hard those talons grip has never actually been measured. The figures that circulate are guesses. The length is on the record, and it's remarkable enough on its own. Out at the edge of the forest, where a river has cut a bank, the morning has a fixed appointment. Macaws and other parrots gather at bare clay. It's commonly said they eat it to cancel out poisons in the seeds and unripe fruit they live on, which is a reasonable guess and turns out not to be what's happening. When researchers looked at the exact layer of soil the birds go for, they found a band running sideways for hundreds of meters along the bank. The birds strip that band and ignore the layers directly above and below it. It came back far higher in sodium than the rest. It's a salt lick. They're after salt, which is genuinely hard to come by on a diet of fruit and leaves a long way from the sea. Watching it happen makes clear what it costs them. The birds don't simply arrive and land. They gather in the trees above, in numbers, and wait. They circle. They start down and pull back up. A bare vertical bank, out in the open, in a crowd, is about as exposed as a parrot ever makes itself. On mornings when a hawk or an eagle turns up, the whole lick gets abandoned, with nobody feeding at all. The hesitation isn't dithering. It's a decision being weighed in the open, and some mornings the answer is no. One more piece of equipment on a bird everyone recognizes. A toucan's bill is usually put down to reaching fruit or to display, and it may be partly both. It's also a radiator. Thermal cameras show the bird deliberately controlling the blood flow into the bill, flooding it to dump heat and shutting it down to keep heat in. The surface is large, the covering is thin, and the blood vessels are right underneath. What it can shift is startling. With air moving across it at around 12 miles an hour, a toucan's bill can get rid of up to 4 times all the heat the bird's body makes at rest. It's a radiator it can turn up and down as it goes, mounted on the front of its own head. And in the morning, warming up after a cool night, the bird can run it the other way and hold the heat in. By now the sun is well clear of the canopy. The isoprene is rising, the fog is gone from the valleys, and the temperature gap between the crowns and the ground is opening up for the day. At midday, the difference between the top of this forest and the bottom of it is as wide as it gets, and how wide it is the thing to hold on to. The climate changes more across 20 or 30 meters of forest, going straight up, than it does across 400 meters of hillside, or across hundreds of kilometers north or south. That isn't a figure of speech. Going from the floor of this forest to its roof crosses more weather than driving for a day. The numbers underneath it are ordinary enough on their own. Up in the crowns, the temperature swings between roughly 20.5 and 27 degrees over a day. Down in the understory, it holds between about 22 and 25. On average, the understory runs more than 2 degrees cooler than the canopy, and the gap gets wider in the rainy season. A closed canopy also keeps the air near the ground about 1.5 degrees cooler than open ground would be, and flattens the daily swing by about the same amount. None of those are big numbers. What makes them matter is that they're stacked on top of each other. An animal living at 30 meters and an animal living on the ground share a hectare and an afternoon and almost nothing else. different temperature range, different humidity, different wind, different light. They're separated by less than the length of a swimming pool. Right at the top, it gets steeper still. Leaves out in the open at the very top of the canopy run 4 to 5 degrees hotter than the air around them on a clear day. They soak up direct sun and can't get rid of the heat fast enough. Leaves a few meters lower, in shade, sit at more or less the temperature of the air. The sharpest part of the whole gradient is exactly where the forest does most of its work. Measuring any of this properly is awkward, because the interesting part is above the trees rather than inside them. North of Manaus, there's a tower for it. Ati-O, the Amazon Tall Tower Observatory, stands 325 meters high, well above even the tallest trees, and it has been measuring what passes between the canopy and the sky continuously since 2015. It records what the forest gives off, what it takes in, and what the air does above it, from a structure taller than anything the forest itself has managed. What that tower is mostly watching is water. The Amazon puts something like 20 billion tons of water into the air every day. The river, over the same day, empties around 17 billion tons into the Atlantic. The forest moves more water upward than the largest river on the planet moves sideways. Different methods give different totals, and the range across studies runs roughly 15 to 20 billion, but the comparison holds anywhere in that range. The water goes up through the trees. Roots draw it out of the soil, it gets pulled up the trunk, and it evaporates away from the leaves. How much one big tree handles is genuinely uncertain. Estimates run from around 500 to 1,200 liters a day, depending on the species, the size, the weather, and how it was measured. That's a wide range, and it should be given as one. The single tidy figure usually quoted is somebody's middle number, with the uncertainty quietly taken out. Some of the water never gets that far. Between 10 and 22% of the rain falling on this forest never reaches the ground at all. It's caught by leaves and bark on the way down, sits there, and evaporates back into the air within hours. As far as the soil is concerned, that rain never happened. What goes up doesn't simply leave either. Around half of all Amazon rainfall is recycled. Water that falls goes back up through the forest and falls again somewhere else in the same basin. One study puts about 20% of Amazon rainfall down to water the forest itself breathed out. In the southwestern Amazon, over Peru and Bolivia, that reliance climbs above 70%. Water crossing the basin turns to cloud, falls, evaporates, and rises again something like 5 or 6 times before it either falls for the last time or reaches the mountains. By the time the air arrives at the Andes, up to 60% of the water in it has been through a tree. Rain falling on a farm in southern Brazil may have passed through several thousand leaves on the way there. That's what usually gets called the flying rivers, and the sums behind it are solid. Water does move west across the continent through the air. The forest does supply a large share of it. The Andes do turn it south, and rainfall a very long way from here depends on it. There's a further claim attached to the same story, and it's worth keeping separate. The biotic pump is the idea that forests don't just recycle moisture, but actually drive the winds. The argument goes that water turning to cloud over the forest drops the air pressure enough to draw damp air inland off the ocean. That would make the forest the cause of the whole circulation, rather than a passenger in it. It's a striking idea, and it gets around widely. It's also a minority view, and it has taken sustained criticism. Published replies argue that the pressure effects are overstated and that ordinary atmospheric physics explains the circulation without it. The disagreement is real, and it isn't settled. So the water sums can be stated plainly and the cause can't. This forest recycles enormous quantities of water. Whether it pulls the ocean inland is an open argument between physicists, and anyone stating it as settled is picking a side without saying so. One more thing gets claimed about all this photosynthesis, and it's worth taking on properly, because it's probably the biggest and most repeated myth about this forest. The common belief is that the Amazon is the lungs of the planet, producing 1/5 of the world's oxygen. It isn't, and it doesn't. The figure that got mangled into that claim is a real one. The Amazon does account for a large share of the photosynthesis happening on land. But photosynthesis is only 1/2 of it. Everything in this forest also breathes, the trees themselves, every animal in them, and above all the enormous crowd of decomposers working through the litter and the dead wood. Breathing and rotting use up very nearly all the oxygen the forest makes. Once both sides are counted, what the Amazon adds to the oxygen in the air is close to nothing. Generous published estimates put it around 6 to 9%, and the mainstream figure is lower still. That isn't a put-down, and it's worth being clear about why. A mature forest in balance is supposed to balance. Making oxygen without using a matching amount would mean carbon piling up somewhere permanently, and in a system this old and this complete, it mostly doesn't. Most of the oxygen in the air came from tiny plants in the sea over an extremely long span of time. It stays there because almost nothing is using it up, not because anything is topping it up. What this forest actually does is more particular and much harder to replace. It moves water on the scale of a continent. It holds an enormous amount of carbon in living wood, and that stays out of the air for as long as the wood is alive. It cools the ground beneath it. It supplies rainfall to farmland thousands of kilometers away. None of that needs an inflated oxygen claim holding it up. And the claim does damage when it falls over, because the correction gets used as proof that none of the rest was true either. By early afternoon, the isoprene is at its peak. The leaves at the top are running several degrees above the air around them. The floor has spent the entire morning at more or less the temperature it held at dawn, and somewhere above the canopy, the day's water is already moving west. The afternoon is the quietest working part of the day down here. Light arrives on the floor in patches rather than sheets, and the patches move as the sun moves. A patch that was lighting one root buttress an hour ago is now lighting the litter beside it, and by dusk it will be gone. Between noon and dusk, the ground itself changes very little. Very little of what happens now is audible from standing height. Most of it happens slowly, and most of it happens out of sight, under the litter, inside a nest, along a trail 2 centimeters wide. Almost nothing on this floor is where an eye would put it. The largest structures are underground, the busiest traffic is the width of a finger, and the richest material in the whole system is a layer of dead leaves that would barely cover a boot. The dirt explains most of the rest. The Amazon grows on some of the oldest and most worn-out soils on Earth. Laterites is the everyday word for them. Oxisols and ultisols are the proper names. They've been ground down over such long spans of time that the things a plant needs have been stripped out of them. Phosphorus, potassium, calcium, magnesium, washed out and carried away. Wearing down on that scale isn't the work of centuries. It's warm rain falling on the same ground for a very long time, dissolving whatever will dissolve and carrying it downhill and out to sea. What's left behind is whatever wouldn't dissolve. Here that means iron and aluminum, which is why the bare earth underneath in this part of the world is so often red. Roughly 3/4 of the Amazon grows on ground like that. Soil scientists have called it a wet desert, meaning that for all the rain, the dirt itself offers a plant almost nothing. The layer of dead leaves says the same thing from the other direction. On the floor of a cooler forest, dead leaves and needles pile up a meter deep or more, because the cold slows the rotting to a crawl, and it all just builds up. Here, that layer runs 2 to 4 centimeters. It isn't that fewer leaves fall. It's that nothing stays long enough to pile up. It breaks the obvious assumption. Thick growth looks like rich soil, and in this forest, the two have almost nothing to do with each other. The forest isn't growing because of the ground. It's growing more or less in spite of it, and the difference is in where it keeps what it has. Almost everything of any value here is already inside something alive. The nutrients are held in wood, leaves, roots, fungi, and animals, and in the thin skin of rotting material between them. They move from one to the next fast enough that very little ever settles into the soil at all. A study that measured more than 34,000 trees went looking for the obvious connection: richer ground, bigger forest, and mostly failed to find it. What was in the soil barely explained the shape of the forest. What did explain it was the recycling. How well a tree pulls its nutrients back out of a leaf before dropping it. How fast the dropped leaf gets taken apart. How much is sitting inside something living at any one moment? That result is easy to push too far. Rich soil does still predict some things. It predicts how fast trees grow and how fast they die, how quickly the whole forest turns over. It just doesn't predict how much forest ends up standing there. Poor ground and rich ground can carry a similar weight of trees at very different speeds. The speed can be measured. A leaf that falls here loses about 30% of its weight in 101 days, and it happens in a set order. Bacteria and other microbes get there first and take the sugars and anything else that dissolves easily, which are the easy calories. Fungi come later because they're the ones equipped for the tough stuff that holds a leaf together, the parts built to resist exactly this. Some of the largest trees on this ground stand on buttresses, fins of wood that flare out from the base of the trunk and can rise taller than a person. The usual explanation is that the trees are shallow-rooted and the buttresses are braces, holding them up against the wind. If that were it, the trees that have them would cluster in windy places and on thin soils, and they don't. What buttresses actually go with is the soil. They turn up most on sour ground that's particularly short of phosphorus, which points away from wind and towards food. The explanation is quiet and faintly comic. A buttress is a wall. Leaf litter drifting across the floor piles up against it, and rainwater running down the trunk collects there instead of running away. Measurements taken in those pockets find more nitrogen and more moisture than the ground a few meters off. The tree has built itself a compost bin and put it exactly where its own roots are. That's an argument rather than a settled fact. It's still a better argument than the wind. Underneath all of it runs the part of the forest that's hardest to see and easiest to get romantic about. The roots of nearly every tree here are wrapped in fungi, and the arrangement is ancient, with both sides genuinely getting something. The fungus threads out through the soil, reaching further than a root can and pulling in phosphorus and other scarce minerals, and the tree pays in sugar. On ground this poor, that isn't so much an advantage as a necessity. The popular version of the story goes a good deal further, and this one is worth taking on properly, because it has spread further than almost anything else said about forests. It says the fungal threads link tree to tree into one big talking network. That old trees push carbon along it to their own seedlings. That a tree under attack sends chemical warnings to its neighbors by the same route. The wood wide web. Part of it is real. Most of it is myth, and the two are worth separating. The real part came in 1997, when a study found carbon moving both ways between fir and birch through shared fungal threads. That finding holds, and the credit belongs where it belongs. The rest traveled a long way past the evidence. A 2023 review went back to the 26 field studies the popular story rests on and checked what later papers had claimed about them. Fewer than half of those claims were accurate. Then there were the experiments that actually tested whether a seedling gains anything from being plugged into an old tree's network. Only about 18% found a gain big enough to outweigh the cost of competing with that same tree's roots. Trees recognizing their own offspring, or sending warnings, has essentially no solid field evidence behind it. And it's the wrong forest anyway. That work was done in cooler northern pine and fir forest, on a kind of fungus that wraps around a root from the outside. Almost every tree in the Amazon has a different partner, an arbuscular one that grows inside the root cells themselves. Different partnership, different job. None of which makes the real version less interesting. A partnership older than forests, quietly doing the work the soil won't do, in a place where the soil won't do much of anything. That's the honest account. It doesn't need the telepathy. The clearest traffic on this floor is a green line moving across it. Leafcutter ants cut leaves into pieces bigger than themselves and carry them back along cleared trails that can run 100 meters and more. The obvious assumption is that they're eating them. They aren't. No leafcutter eats a leaf. The leaves go underground, into chambers where the ants chew them to pulp and feed the pulp to a fungus. That fungus, Leucoagaricus, is the actual crop. It grows on the chewed-up leaf material and puts out swollen, food-rich knobs, and those are what the colony eats. The ants weed it, feed it, keep the damp right, and take out anything that doesn't belong. It's farming in the full sense, and the ants got there tens of millions of years before humans did. The scale is easy to underestimate from the trail. A grown colony can hold several million ants. The gardens sit 1 to 2 meters down, but the digging goes far deeper. Some shafts run tens of meters, possibly as far as the water table, and the whole thing is built to breathe. A trail watched for long enough turns out to be more organized than it looks. Cutters working above, carriers coming back below, and the path itself cleared and kept clear. The surface is scraped down to bare earth and kept that way, and a colony will hold the same route for a long time. A leafcutter highway is a built thing, not just the easiest way through. From a little above, it's a green seam moving through the litter, and the green is only traveling one way. A farm that size, growing one crop in a warm, wet chamber, has the problem every single crop farm has. The pest here is a mold called Escovopsis, which lives on this fungus and nothing else, and which will take a garden apart if it gets a hold. The ants' answer is the part that stops people short. They carry their own pesticide on their bodies. The white waxy bloom on a leafcutter's shell is a colony of bacteria. They're Streptomyces, the group that gave human medicine a large share of its antibiotics. It lives on the ant, and it makes compounds that hold the mold down. The ant is the ground it grows on. The bacteria do the chemistry. It goes further than one compound. A single strain has been found making several different antifungals at once, including candicidin. That isn't waste. It's insurance. A mold that evolves its way around one compound still has to get past the others. And some colonies take an entirely different route. Their bacteria pump out ammonia until the garden is too alkaline for the mold to grow, which isn't a drug so much as a change of climate. How much leaf all of this gets through is genuinely disputed, and the disagreement is worth keeping. Measured across a whole forest, leaf cutters take something like 2% of the leaves grown in a year. Measured inside the patch one active colony works, the figure climbs to 10 or 15%. Both numbers are real. They're answers to different questions. The column running now, in the afternoon, is thinner than the one that ran this morning. That's a real pattern, and heat isn't the explanation. When their foraging was compared at matched temperatures, morning still beat evening. Time of day is doing something on its own, whatever the warmth is doing, which quietly complicates the assumption that insects are thermometers with legs. The other column on this floor works in a completely different way. Army ants have no fixed nest. The colony is the nest. At rest, the workers link legs and bodies into a hanging mass called a bivouac, with the queen and the young held inside it. When the colony moves, the building walks. A bivouac isn't a figure of speech. It's a physical object made out of the colony's own bodies, slung under a log or a root or a low branch, layered thick enough to hold a steady temperature inside. There's no wood in it and no soil. Nothing in it was anything but alive an hour ago. The front running now left its bivouac at first light and has been pushing on since. It isn't a line but a sheet, a swarm front that can spread 25 meters wide, moving across the litter and taking everything it can overpower. Over a day, a colony of this kind takes something like 100,000 insects and spiders, and colonies run up to about 2 million workers. What makes the swarm interesting isn't the killing, it's the crowd. More than 500 other species have been recorded living off these raids: beetles, mites, flies, a blind snake that follows the columns, and a long list of specialists that exist because the swarm exists. It's the biggest gathering of animals around one thing known anywhere on Earth, built entirely on the disturbance one moving predator kicks up. The clearest example is in the air. Between 16 and 29 Amazon bird species, mostly antbirds, are obligate ant followers. They aren't eating the ants. They're eating what the ants flush out, the insects that break cover ahead of the front and fly or jump straight into a waiting beak. Obligate is the word that matters. because these birds struggle to feed themselves without a swarm to work. They aren't following food. They're following a machine that makes food. Genetic work suggests the habit is old, up to 6 million years of birds building their lives around the movements of ants. The swarm isn't simply a hunting party crossing the forest. It's a traveling event with a permanent audience, and it has been on the road since long before there was anyone to notice it. The raid has a limit built into it. The colony switches between 2 phases, each running roughly 2 to 3 weeks. In the wandering stretch, the young are growing and hungry, and the bivouac moves almost every night. In the settled stretch, the queen lays, the young turn into adults, and the whole thing stays put. So ground a swarm has crossed tends to get a long gap before anything like it comes through again. The colony isn't working a rotation though, and doesn't come back to a stripped patch on any kind of schedule. Underneath the traffic anyone can see, most of the actual demolition is done by termites, and Amazon termites don't all do the same job. Termite work is almost entirely invisible from standing height. It happens inside dead wood, under the litter, and in tunnels that never open to the surface at all. They split into feeding groups. Some work on solid wood, some on rotting wood, some on the leaf litter, and some straight on the soil and whatever is already mixed into it. That split isn't just something people have watched. The chemistry of a mound carries the mark of what the group that built it was eating. What a colony has been living on can be read back out of the structure it left behind. Between the termites, the fungi, and the microbes, the reason the litter here is 2 centimeters deep rather than 2 meters is simply how much machinery is pointed at it. There's a second wave working on what the first wave leaves behind. A seed that has passed through an animal lands on the floor inside a pile of dung, which is easy to spot and which every seed-eating rodent in the neighborhood can find. Dung beetles get there first. Within hours of a dropping arriving, they've broken it up and buried it, and the seeds go down with it, out of sight, out of reach, and in contact with soil. It matches up by size, and that matters. Bigger beetles move bigger loads and bury bigger seeds. Big dung beetles are also among the first things to go when a forest is disturbed. When they vanish from a patch, the trees that stop getting buried first are the ones with the largest seeds. Those tend to be the slow-growing, long-lived, carbon-heavy ones. The beetle is small, and what follows from it isn't. None of this is planned. The beetle is burying food for its own young, and the seed is just along for the ride. It simply happens that the safest place in this forest for a large seed is a few centimeters underground, and that something else here is already digging. By late afternoon, the floor looks unchanged. The same patches of light have moved a little further along the same ground. The litter is where it was. Underneath it, across one afternoon, several million leafcutters have delivered a crop. A swarm front has crossed a stretch of ground and taken it apart. Beetles have buried a day's worth of seed. A fallen leaf somewhere is a fraction further along its 101 days. The forest standing above is built out of that. Not out of the soil, which gives very little, but out of the speed at which everything here is handed from one body to the next. The light changes before anything else does. Through the middle of the day, the sun comes almost straight down, and the floor gets what little it gets in scattered coins. In the last hours, it arrives at an angle, and the angle is what matters. It reaches sideways into the understory, under the roof rather than through it, and for a while the trunks are lit from the side instead of the top. It doesn't last long. This close to the equator, the sun goes down fast, and the gap between full light and dusk is measured in minutes rather than in the long evenings further north or south. Somewhere within a few hundred meters, a tree has come down. It may have happened this year or a decade ago, and the signs are much the same either way. A hole in the roof, a shaft of direct light reaching the ground, and underneath it, a patch of forest behaving completely differently from everything around it. The gap is how this forest renews itself. The idea was set out in 1947 by a botanist named Alex Watt, who described forest not as one steady thing, but as a patchwork, each patch at a different stage of the same cycle. Grown canopy is one stage. A gap is another. Every part of the forest is somewhere in the loop, and it's the loop that lasts rather than any particular tree. What happens inside a gap is a race. Light on the floor is the scarce thing here, and when a shaft of it opens up, the seedlings already waiting underneath get a chance they won't get again. Fast starters move first, species built for exactly this, growing quickly and cheaply and not for very long, reaching straight for the hole. Beneath them, the slow shade lovers climb at their own pace, and they'll still be alive long after the fast ones have died. Usually the gap closes over and the patch rejoins the canopy. A gap is also where the insect life of this forest becomes obvious. Butterflies gather where light reaches the ground, and Manu National Park, over on the Peruvian side, has more than 1,300 butterfly species recorded on its own. A light gap is where a person is most likely to meet a good number of them at once. Not every gap closes. Lianas can take one over. A liana is a woody vine, and the important thing about it is what it doesn't build. It doesn't build a trunk. It uses somebody else's, climbing a tree that's already there, letting that tree's wood carry its weight, and spending everything it saves on leaves instead. The result is a plant with far more leaf for the amount of stem than any tree can manage, sitting on top of a structure it didn't pay for, taking the light first. That's expensive for the tree underneath. Trees carrying heavy loads of vine die at rates around 30% higher than trees without them, and grow around 35% more slowly. The big trees hold most of this forest's carbon, so the sums run straight from the vine to the sky. In a fresh gap, with light everywhere and nothing tall left to shade them, lianas can move faster than anything else and lock the patch down. What follows is a dense tangle that holds down the tree seedlings underneath and keeps the hole open for decades. That state is stable, and it's where the impenetrable jungle of the films comes from, the green wall, the machete. It genuinely exists. It's just a sign of damage, rather than the normal state of this forest, and standing in it is nothing like standing under closed canopy an hour's walk away. Among the tallest trees on this ground is one carrying a story with more moving parts than almost anything else here. Vridi, the Brazil nut tree, stands well clear of the canopy around it and lives for centuries. Its flowers are where the complication starts. Each one is closed by a coiled hood of tissue, and the hood is locked shut. A bee has to be big enough and strong enough to physically force it open to reach the nectar inside. Most insects can't. Nearly all of the work is done by female orchid bees of the genus Euleima, which are big enough and powerful enough to lever the hood up. So the tree depends on one particular bee, and the bee depends on something else entirely. Male orchid bees don't pollinate the Brazil nut. What they do is collect scent. They visit particular wild orchids, Stanhope, Cassitium, and others, scrape the fragrance off the flowers, and store the mixture in hollow pockets in their back legs. They spend a great deal of their lives doing this. For decades, nobody could say why. The answer arrived in 2023. Experiments showed that males carrying richer, more complicated blends mate more often and father more young. The perfume is a display, but a collected one, gathered from the forest rather than made by the animal. A male orchid bee is advertising how well he forages, using somebody else's chemistry to do it. Which means the chain runs backwards in a way that's easy to miss. No wild orchids, no scent for the males. No scent, no mating. No mating, no females. No females, no bee strong enough to open the flower. No Brazil nuts. The far end of the chain is on the ground. The fruit is a woody pod about the size of a grapefruit and roughly as hard as a cannonball, holding a dozen or more seeds sealed inside. It falls 30 or 40 meters and doesn't break. Almost nothing in this forest can open it. The agouti can. It's a rodent about the size of a rabbit, with teeth up to the job, and it's one of very few animals that will get through the pod at all. Having opened it, the agouti eats some of the seeds and buries the rest, one at a time, scattered over a wide area to come back for later. It doesn't come back for all of them. The forgotten ones are the next generation of trees. That habit, scatter hoarding, turns out to be what most reliably moves seeds off the ground directly under the parent tree. That ground is where a seed is least likely to survive. The diseases and seed eaters that specialize in one kind of tree gather under a grown one of that kind, and the odds down there are poor. A rodent with a patchy memory is what solves it. All of which explains something about how Brazil nuts reach a shop. They've never worked as a plantation crop. Planted in rows away from real forest, the trees grow and flower and set almost nothing. The orchids aren't there, so the bees aren't there, and there's no agouti to bury whatever does fall. Nearly every Brazil nut sold anywhere in the world was gathered from a wild tree in standing forest. It's one of the few foods traded worldwide that can't be farmed, and so it lasts only as long as the forest does. The figs run a version of the same arrangement, older and stranger. A fig isn't really a fruit. It's a flower head turned outside in, a hollow chamber lined on the inside with hundreds of tiny flowers, sealed almost shut with one narrow entrance. Nothing can pollinate it from the outside. The pollinator goes in. A female fig wasp forces her way through an opening barely wide enough to let her past, and there's no way back out. Inside, she lays her eggs and pollinates the flowers with pollen she carried from the fig she was born in. Within a day or two, she dies there. Her young hatch inside the chamber, mate inside it, and the new females leave carrying pollen to begin again. How exact the match is the remarkable part. There are more than 750 kinds of fig, and broadly, each has its own kind of wasp, which pollinates that fig and no other. The two have been tracking each other for somewhere between 60 and 75 million years. That's a partnership older than the Amazon basin in its present form, and older than most of the mammals now living in this forest. Across the whole forest, figs matter for a plainer reason. Between them, those 750 kinds feed something over 1,200 species of bird and mammal. And they don't all fruit at once. Most trees here fruit by the season and more or less together, which makes gluts and then long, lean stretches. Figs fruit at odd intervals, out of step with everything else and with each other. In the lean months, a single fruiting fig may be the only real food for a long way around. That makes a scattered handful of trees the thing carrying a large part of the animal life through the gap. Some of them get there by killing. A strangler fig starts as a seed in bird droppings, dropped into a fork high on another tree's trunk. It sprouts there, up in the air, and lives for years on the debris that has collected around it. Then it sends roots down the outside of the host trunk towards the ground. When those roots arrive, the plant's growth changes completely because it isn't living on scraps anymore. The roots thicken, spread around the trunk, and join where they touch, until the host stands inside a cage. Above, the fig's crown grows out over the host's own and takes its light. The tree is being shaded from above and squeezed from below at the same time, and the whole thing takes somewhere around 50 to 70 years. Around 150 species in the Amazon live this way. The ending varies more than the name suggests. Many hosts do die and eventually rot out, leaving the fig standing as a hollow tube around the space where a tree used to be. But some hosts survive for decades inside the cage, growing on, wrapped up, and apparently untroubled. The strangler is a slow competitor rather than a reliable killer, and the difference is worth keeping. Late afternoon is also when a particular sound comes back. Oropendolas are large canopy birds that build hanging woven nests, long dangling bags, hung in numbers from the same tree. The display that goes with them is physical. A male on a branch bows forward until he's hanging almost upside down, wings spread, and lets out a liquid gurgling call that runs downward and then breaks. It's one of the more recognizable sounds in this forest, and it's most reliable in the early morning and again now, which makes it a fair clock. There's a boundary out at the edge of this ground, and in the late afternoon it's within a walk. The terra firma ends where the land drops away. Below the drop is floodplain, and the floodplain isn't dry. Once a year, the river comes up into it. Not as a flood in the disaster sense, but as a slow, predictable yearly rise and a fall again on the same schedule. The size of that movement is the part that's hard to believe. Water levels swing by around 10 meters through the year in the central Amazon, and by as much as 14 in places. That isn't a river spilling over its banks by a foot or two. It's the whole surface of the water rising the height of a 3-story building and then coming back down every year on time. The forest below the line lives inside that. Some of it stands in water for as much as 270 days a year, 3/4 of its life underwater, with the trees alive throughout. It's a different forest with different species, and it isn't this ground. The way to make sense of it was set out in 1989 by Junk, Bailey and Sparks, who argued that a river and its floodplain aren't arranged in fixed zones at all. They're arranged around the pulse, the yearly rise and fall, and nearly everything living there is timed to it. Where the two forests meet, the animals sort themselves out. Some go down into the flooded forest as the water comes, and some come up out of it. At the edge, in the low riverside growth, is a bird that doesn't quite belong to either. The hoatzin eats leaves, which almost no bird does, because leaves are difficult and slow. Its answer is a cow's answer, an enlarged crop and gullet where bacteria ferment the leaves before they're digested. That chamber takes up something like 77% of the bird's gut. The cost is flight. The fermenting vat sits more or less where a bird's flight muscles need to attach, and the hoatzins are shrunken to fit around it. It flies badly and briefly, and mostly it clambers. It's a plain trade, the ability to eat what nothing else is eating, paid for with the thing birds are otherwise for. Back up on the dry ground, the sorting follows a clear rule. Agoutis, brocket deer, curassows and peccaries all turn up less often in flooded forest when the water is high. They pull back uphill and wait. One animal has no choice in the matter at all. Giant armadillos live in burrows, and their burrows are only ever found in terra firma, because a burrow underwater isn't a burrow. They can't climb out of the flood, and they can't swim out of it. Unflooded ground isn't a preference for them. It's the whole of the world available to them. The light goes flat, and then it goes orange, and the angle that reached in under the canopy an hour ago is gone. What's left is the long green half-dark that will hold for the rest of the evening. The light doesn't fade here so much as switch off. This close to the equator, there's no long evening. The sun drops at a steep angle, the last of it leaves the canopy, and within a few minutes the forest goes from readable to not. What follows is the loudest changeover of the day, and it runs the opposite way to the mornings. The same 2 years of recording that showed insect noise at its lowest around midday show it rising through the afternoon and peaking at dusk. Both the volume and the number of different calls are higher at night than at any point in daylight. So the forest isn't settling down. It's handing over to the shift that makes most of the noise. Inside that, there's a second handover almost nobody hears as one. Cicadas call by day, and some of them push on into dusk. Crickets and katydids keep to full darkness. The two groups overlap in a narrow band of pitch, and where two signals share a pitch, they get in each other's way. A call that can't be told apart from another call doesn't do its job. So they take turns. One group finishes as the other begins, and the join between them lands close to the moment the light goes. The cicadas do the same thing among themselves, in finer detail. Different species stagger their calling times across the stretch from 7 in the morning to around midnight, each with its own slot. It isn't teamwork in any deliberate sense. It's what happens when species that need to be heard grow up alongside each other for long enough, a timetable, arrived at by everyone avoiding everyone else. The frogs start when the light finishes, and they get loud. A frog call isn't made by breathing out. The animal moves the same air back and forth between its lungs and a stretchy sac in its throat, driving it across the vocal cords in both directions. So the call can run on without stopping for breath. The sac itself is the amplifier. Its size and shape set both the pitch and how far the sound will carry. That's why frogs that look much alike can sound nothing alike, and why a very small animal can be heard a long way off. Something larger is moving now as well, and it has been moving on and off all day. Jaguars are cathemeral, which means they're active in daylight and in darkness both, with the peaks around dusk and again around dawn. So this is one of the two windows when a jaguar is most likely to be moving. Females with cubs are the busiest of all, out for something like 13 hours a day, because they're hunting for more than themselves. The kill is unlike any other big cats. Lions and tigers suffocate, a grip on the throat held until the animal stops. A jaguar goes through bone. It drives its canines straight through the skull between the ears, or between the bones at the base of the neck, and the prey is dead at once rather than several minutes later. It can do that because of its bite, for its body size, the strongest of any big cat. There's also a cat here that a great many people picture, and the common belief about it is a myth. A black panther isn't a species of its own. It's a color, an excess of dark pigment which turns up in jaguars and in leopards on opposite sides of the world. The gene behind it is recessive in leopards, so both parents have to carry it, and dominant in jaguars, where one is enough. And the animal isn't actually black. In good light, or at the right angle, the rosettes are still clearly there under the dark coat, like a pattern printed on dark cloth. In the branches, the night's first shift is already out. The kinkajou is awake almost the whole night, but not evenly. It's busiest between about 7 in the evening and midnight, and then again in the hour before dawn, which puts it right across both shift changes, at each end of the darkness. It moves through the canopy on a gripping tail. It's also hard to pin down by diet, because it belongs to the carnivores and lives mostly on fruit and nectar. And on a broken stump somewhere, something that hasn't moved all day is about to. The common potu spends the daylight hours sitting upright and motionless on top of a snapped branch, eyes narrowed to slits. Its feathers match dead wood so exactly that it looks like more of the stump. It isn't hiding behind anything. It's being a piece of the tree out in the open for 12 hours. At dusk, it opens its eyes and starts hunting, from that one perch, taking insects out of the air and coming back to the same spot. The call that goes with it is a slow falling run of notes, mournful in a way that has gathered a great deal of local folklore around it. In parts of the Amazon, the bird is known as the ai mama, which is the sound written down. The insects are at full volume now. The frogs are going. The last of the day birds have stopped, and the temperature has already started to drop. Sound travels further at night, and the reason is the same one that put fog in the valleys before dawn. The floor cools faster than the air above it once the sun is gone. That puts a layer of cooler air underneath a layer of warmer air, which is the other way round from the daytime. Sound moving upward through that join gets bent back down instead of escaping. The forest gets a lid on it. A call that would have faded off into the sky at midday is sent back to the ground and carries on sideways. Everything is heard from further away at night than the same sound would be at noon. What comes of that is a soundscape with depth in it. Close sounds and distant sounds arrive together, layered, and it becomes very hard to judge how far away anything is. A single frog 3 meters off and a chorus 400 meters off can seem to sit in the same place, which suits what's flying. There are more than 160 kinds of bat in the Amazon basin, around 1/10 of every bat species on Earth, in one river system. Local surveys often record more than 100 kinds in a single patch of forest. They aren't variations on a theme either. They eat fruit, nectar, pollen, insects, frogs, other bats, fish, and blood, and the equipment differs to match. In one night's netting at a single site, a researcher may handle 12 kinds that share little beyond the ability to fly in the dark. Two very common beliefs about bats are myths, and the first one is in the phrase itself. Bats aren't blind. Most of them see perfectly well, and some fruit bats see in low light around 3 times better than a person does. Echolocation runs alongside their eyes rather than instead of them, and a bat in flight is generally using both. They also aren't simply reacting to whatever comes back in the echoes. Wild bats that have been tracked find their way across areas kilometers wide using a map they carry in their heads. Pipistrelles taken away from their roost found their way home across a 3-kilometer radius on echolocation alone, getting it right something like 95 times out of 100. They aren't feeling their way along. They know where they are, and they know where home is from there. Over the water at the forest edge, one of them is doing something almost nothing else does. Only 2 kinds of bat in the world are confirmed fish eaters, and the greater bulldog bat is the one here. It flies 20 to 50 centimeters above the surface, low enough to touch it, with big hooked claws on its back feet trailing in the water or just above it. The problem it has solved is that its sonar doesn't go through the surface. A fish below the waterline is invisible to it, so the bat isn't listening for fish. It's listening to the water, reading the ripples a fish makes just underneath, and the split second when a fin or a back breaks through. It calls in bursts, builds a picture of the surface, and rakes its claws through the spot where the ripple was. What it catches goes into cheek pouches, to be eaten later in the air or on a perch. Elsewhere in the dark, something is drinking. The tube-lipped nectar bat has a tongue about 8.5 centimeters long, roughly 1.5 times the length of its whole body. A tongue that size won't fit in a head, so it isn't kept in one. It reaches down into the animal's ribcage, coiled around the base of the heart, and unrolls out through the mouth when the bat feeds. It's the longest tongue for body size of any mammal, and it exists because one particular flower is that deep. The flowers are built for this from the other end. Bat-pollinated blooms in this forest only open after dark. They're pale or white rather than colored, because color is no use at night, and a pale surface shows up against dark leaves. They give off a heavy fermenting smell, closer to overripe fruit than to perfume, which carries in still air. And they hold a lot of watery nectar rather than a little strong nectar, because the animal they're paying is large and costly to run. The kapok goes further than that. Before it flowers, it drops its leaves entirely, and then blooms at night on bare branches. A crown with no leaves is an open crown, and an open crown is one a bat can fly into and out of without hitting anything. The tree isn't only advertising, it's clearing the runway. Bats aren't the only pollinators out here. The kinkajou, which belongs to the carnivores, laps nectar with a long tongue and carries pollen from flower to flower on its face and chest. It's the only member of the whole carnivore family known to pollinate anything, a group defined by eating meat, with one member quietly working the flowers. And then there's the one everybody has heard of. Vampire bats don't suck blood. The name has done a lot of the damage there. What happens is that the bat lands near a sleeping animal, usually a large one, and walks. Vampire bats are unusually good on foot and can run along the ground. It finds a spot and makes a very shallow cut with its front teeth. Then it laps. It can stay there lapping for up to half an hour, taking something like a couple of teaspoons, and its spit contains a blood thinner that keeps the cut open while it feeds. The animal it's feeding on often never wakes up at all. Finding the spot is the hard part, and it's done with heat. Around the nose, the bat has special nerve endings, carrying an altered version of a sensor called TRPV1, retuned to fire just above normal body temperature. In every other mammal, that sensor registers painful heat. In this one, it's been turned into a detector for warmth. It can find a vein close to the surface of a sleeping animal's skin from as far as 20 centimeters away, in complete darkness. The bat isn't searching. It's reading a heat picture and going to the warmest line on it. The part worth stopping on is what happens back at the roost. A vampire bat that misses a meal can starve in about 2 days. That's a brutally thin margin, and in a colony where somebody fails every night, it would be killing bats constantly. So they feed each other. A bat that has fed will bring blood back up for a roost mate that hasn't. They do it for relatives, which is no surprise. They also do it for unrelated bats that have fed them in the past, and they favor those ones over others. That's a favor returned, tracked over time, between animals with no family stake in one another, one of the clearest recorded cases of that kind of food sharing in any wild mammal. The insects at this hour are worth stopping on too. In the Amazon, a moth has been photographed drinking the tears from the eye of a sleeping bird. It lands close, slides its feeding tube under the eyelid, and drinks while the bird sleeps through it. The habit is called lacryphagy, and the reason for it looks like the same reason the macaws go to the clay bank. Tears carry sodium and protein, both scarce here, and a bird's eye is a small, reliable source of both. Other moths are fighting a war. Tiger moths make ultrasonic clicks from a patch on the middle of the body, pitched inside the band bats used to echolocate. In controlled trials, moths whose clickers were silenced were attacked roughly 4 times more often than moths left alone. The clicks are jamming, filling the returning echo with noise at exactly the moment the bat commits to a strike. An arms race run entirely above the range of human hearing, in the dark, at speed. On the ground, the hunting is quieter. Ocelots do almost all of their hunting after dark, by stalking and ambush rather than chase. What's striking about them in this forest is how much one differs from the next. Home ranges recorded in the Brazilian Amazon run from under a square kilometer to around 90. That's a 90-fold difference inside one species in one region. It follows how much prey there is and how much competition, rather than anything about the animals themselves. They can be counted because every ocelot's coat is unique. The pattern of rosettes and blotches works as a fingerprint, so an animal photographed by a camera trap can be recognized again years later at a different camera. One central Amazon record covers 899 camera stations across 7 years, and the animals in it are known individuals rather than a tally. At the water's edge, a black caiman lies with only its eyes and nostrils above the surface, the rest of it out of sight. Behind its retinas is a tapidum lucidum, a mirror layer that bounces incoming light back through the light-sensitive cells a second time, which nearly doubles what it can do with whatever moonlight there is. The side effect is eye shine. A torch swept across a river at night comes back with dozens of red points in it, all of them looking back. Above, the owls are working. The speckled owl is the largest owl in tropical America, and its prey list is longer than its size suggests. It takes bats, rodents, and opossums, and it also takes animals bigger than itself, including three-toed sloths and small monkeys, hauling them off branches in the dark. It isn't the only one up there. At least 9 kinds of owl live in this forest, divided up by size, by prey, and by where in the height of the forest they hunt. The spectacled owl is simply the one big enough and loud enough to get noticed. Nothing about the night down here is still. It's only that the movement has become almost entirely sound and heat, animals finding each other by ear and by warmth, in a stretch of forest where sight has stopped being the sense that matters. By now, the temperature has dropped several degrees from its afternoon peak. The humidity is climbing back towards saturation, and the loudest hours of the whole 24 are underway. The coldest part of the night is the last part of it, and by this hour, the forest has given back most of the heat it took in during the day. The temperature swing across one day here runs somewhere between 8 and 12 degrees, which is a wider range than the gap between the wettest season and the driest. Where a cooler forest has a year with seasons in it, this one has a day. Ecologists have taken to calling the cool, damp, small hours the winter of the tropics. The phrase is more literal than it sounds. For a great many animals here, the night genuinely is the cold season, and it comes round every 24 hours. The damp goes the other way. It never really drops. Even in the driest months, the air stays above 77% humidity, and in the wet season, above 88%. In the hours before dawn, it's at its highest, which is why the leaves are wet and why the fog is already forming in the low ground without a drop of rain having fallen. There's a monkey awake in all of this, and it's the only kind there is. The night monkeys, AOTUs, are the only truly night-living monkeys on Earth. Every other monkey, everywhere, is a daytime animal. This one group went the other way, and their equipment tells the story of a compromise rather than a clean solution. They don't have a tapetum lucidum. The mirror layer behind the retina that gives a caiman or a cat its eyeshine simply isn't there. The whole primate line lost it a long time ago, and this group never got it back. So there's no shortcut. What they have instead is size. Very large eyes for the size of the head, and a retina packed with rod cells, which are the ones that work in low light. What they give up for it is color. Night monkeys are completely colorblind. They live in a world bright enough to move through with no color in it at all. Because the light they're using comes from the moon runs their lives. That has been measured, and the numbers are the strongest anywhere in this part of the record. Wild owl monkeys tracked across a full lunar cycle were more than twice as active at full moon as at new moon. That's around 52% of their daily activity under a full moon, against 26% under a new one. They aren't mildly affected by moonlight. They're running on it. The proof came from an eclipse. During a total lunar eclipse, with the moon going dark over an hour or so, the tracked animals almost entirely stopped moving. Not gradually, and not because anything else had changed. The temperature, the damp, and the hour were all where they should have been. The light went, and the monkeys stopped, and when the light came back, they carried on. Moving in the dark as a family means staying in touch, and they do that with sound. Up to 8 different kinds of call have been described, which is a decent working vocabulary for animals that can't see each other well and can't afford to get separated in a forest at night. Down at ground level, some of the darkness isn't entirely dark. Glowing fungi are lit all the time, not flashing, not switched on by anything, just on, day and night, with the daylight washing them out. Only about 115 kinds are known worldwide, which is a small number set against all the fungi on the planet. Only 2 of them have been described from the Amazon basin, Mycena lacrymans and Mycena christinae. The glow is faint, greenish, and easiest to find on rotting wood on a night with no moon at all. Why they do it isn't settled. The leading suggestion is that the light draws in insects, which then carry the spores away, and there's some experimental support for it. But it's an idea rather than a finding, and there are glowing species it doesn't obviously fit. What is settled is the chemistry, and it's stranger than the question it answers. The reaction that makes the light needs 2 parts, luciferin, which gets used up, and luciferase, which burns it. Across glowing creatures with nothing else in common, those 2 parts are often interchangeable. The luciferin from one branch of life will react with the luciferase from another in groups that haven't shared an ancestor for an immense stretch of time. The same ancient chemical trick has been picked up again and again, separately, by things with almost nothing else in common. Some of the light down here isn't fungal. Brazilian railroad worms are the young and the young-looking adult females of a beetle, and they're the only land animals known to make genuinely red light. Almost everything else that glows on land is yellow-green. These carry a row of yellow-green lights down each side and red lanterns at the head and the tail, and they run both at once. That takes 2 chemically different luciferases in the same animal, tuned to give off different colors, one body with 2 separate lighting systems fitted in it. The click beetles do something different again. Where a firefly flashes, Pyrophorus simply stays lit, a steady glow rather than a signal. And they can turn it up, disturb one, and it gets brighter. In the southern Amazon, Pyrophorus angustus gives off an unusual orange light rather than the usual green. How much of this is still uncounted is worth saying plainly. A completely new group of firefly, Haplocada, found nowhere but the Amazon, was described in 2022. Not a new species inside a known group, but a whole new group. This isn't a finished list. It's an ongoing one, and the things still being found aren't obscure specks under a microscope. They're beetles that light up. The temperature is at its lowest now. The cold air has been sliding downhill for hours and is sitting in the valleys. On the leaves, the switch has already happened, and water is condensing out of the air onto foliage that spent the whole day losing it. The insects are still going. They will go for a while yet, and the first birds will start above them, in the crowns, some 40 minutes before anything down here begins. Above the canopy, the sky has started to change color. On the floor, it is still completely dark, and it will stay dark for some time after the sky has finished. And that's where we'll leave the Amazon tonight. The forest carries on without us. The bats are still reading the water. The moths are still finding their way by scent. Under the leaf litter, the ants are still carrying their cuttings down into the dark. None of it needs anyone watching. If you're somehow still awake, thank you for spending these last few hours here. There's a whole planet still to get to, and a great many of its secrets with it. Another episode will be waiting whenever the next sleepless night comes. For now, though, there's nothing left to do. Let your thoughts wander wherever they like. Sleep well.